basically this presentation I would like to cover the laser remote sensing for the study of atmosphere, and also some of the instrumentation associated with these techniques, because I have been working in the Department of Space, in the VSSC. So at that time, the Lidar systems were basically something like made for the laboratory there. So they were not commercially available. So anybody who is interested, any group interested in the department, the laser remote sensing, they have to develop their own laboratory facilities in this area. So we started in somewhere in 80, development of a radar system, and perhaps that was the first group in the country to produce results on aerosols profiles in making use of this system developed in-house there. So later we moved on to other second generation and third generation LiDAR systems also. And we spent a lot of time in developing the systems themselves, because in many other places it is not available. So commercially, the systems were available only for lower atmosphere studies. So otherwise, the systems what we had developed, the cost was very high, and also the size of these systems are to be quite large. So that is why only a few organizations were able to start the activity by developing their own. So then later on, we moved on to after my superannuation, I joined the University of Kerala as a visiting professor. And then we had a funded project from Department of Space for 3 years, mainly to study the interaction of clouds and aerosols in the atmosphere by making use of laser remote sensing techniques there. So in that, we could do some good work. So then we published some papers also in that one. But then after that, I moved on to shifted to Hyderabad, and I was there with one engineering college where we also had a funding from Department of Science and Technology for mainly on the development of the LiDAR itself, and then also conducting some scientific studies. So in this talk, basically, I will be presenting some of the results which were obtained when I was in VSSC, also when I was in more in the Kerala University, and some new results when I was in one of the colleges here. But then after that, for the last 3-4 years, I have been working with Ananth Technologies, which is an industry interested in the technology development. So being aware of what is required from the science point of view, so I could really conceive what are the systems required for any scientific group or application oriented in the LiDAR area. So for the last 4 years, we have been working on the technology development in this area. And I would like to say that the science in the laser remote sensing is basically technology driven. Because to start with, the laser remote sensing was being done by making use of the white light, the searchlights, because there was no laser available at that time. So in other countries, they have been working on the remote sensing by making use of very high powerful searchlights. And then being a white light, naturally, the signal to noise ratios are very low. So one could reach only a few kilometers making use of that kind of sources there. Then the advent of laser, then the first, I think the laser remote sensing was in the forefront to make use of the laser properties for the remote sensing purpose. So then onwards, still, as I said earlier, the development activities were being done by individual groups to suit for their research interests in the basic studies of the atmosphere. So that way it went on for some time. And then in some research institutes like IISc and all, they could start a program making use of some low-end LiDAR systems commercially available at the time. Today, of course, there is a lot of the developments in the technology, both in terms of laser sources, the data power, compactness, similarly on the receiving side, and detectors, we have new technologies come, and then the more sensitive detectors, even to measure very low light levels, and then the signal processing. So all these things have really improved, rather advanced the applications of laser remote sensing to a new heights here. So in my talk, though I have been, I just start with the background of the information on the scientific studies, what one can think of making use of laser remote sensing. But I will be touching more on the technology part of it, and then still I will be presenting some of the results which have been done earlier. So right now, for the last 4 years, really, I don't have good results, scientific results to present in this forum, though I am been interested in developing systems and then making use of them for the scientific studies there. So can I have the so now the is almost yeah, this is what I said. Next. Now the talking about the Earth's atmosphere, the composition of the global atmosphere is changing because of the human activities. So climate models predict the global warming due to carbon dioxide and other greenhouse gases. But then the uncertainties in the modeled radiative effects of aerosols and clouds make the predictions inaccurate. Because the aerosol particles or clouds are highly variable, both temporally and spatially. So unless you have a real models, the accurate models, you'll not be able to predict what is the effect of these aerosol particles or clouds in the atmosphere. So aerosols are basically the tiny particles suspended in air, either in the solid phase or solid liquid phase. The aerosols range in size from around 10 nanometers upward to 100 microns. The majority of them are derived from the natural sources like vegetation, sea spray, volcanic eruptions, and so they contribute about 90% of the aerosol particles in the atmosphere are contributed by the natural activities there. But now it is estimated that more than 10% are generated by human activities, such as burning of fossil fuels, industrialization, urban transport to automobiles, etc. Now, the importance of the aerosol particles are coming up because the man-made anthropogenic aerosols are increasing in number, so the contribution is increasing all over global level. Earth atmosphere consists of basically the aerosol particles in what you call solid particles, and then also we have simultaneously the molecules in the atmosphere, neutral atmosphere consisting of nitrogen and other gases there. So in the lower atmosphere, basically we have the composition of aerosol particles as well as the gas molecules in here. Now the aerosol effect on the global climate directly through scattering and absorption of incoming solar radiation, and indirectly through the formation of cloud condensation nuclei. So these solid particles will be contributing directly and as well as indirectly for modifying the solar radiation reaching the Earth here. So the next slide. So the relative impacts of natural aerosols and those of human origin are poorly understood, and it is also not clearly known as of now whether aerosols are cooling or warming the Earth. Because depending upon where they are located and their composition and the size distribution, these things alter the effect of the aerosol particles in the climate. Sometimes some of the aerosol particles will warm up, some of them will cooling the Earth's atmosphere. Similarly, the another important constituents of the atmosphere are the clouds. They are the key regulators of the planet's average temperature. Some clouds contribute to cooling because of they reflect back the solar energy back to space in the shortwave radiation. Whereas some of the clouds contribute warming because they act like a trap what is coming from the ground after the infrared radiation. So the clouds act in two ways. One is cooling, another is warming up. So thus the aerosol particles together with thin transparent clouds play a major role in regulating the Earth's air quality and climate. So the thin clouds which are around the tropopause, they contribute both in terms of cloud warming as well as cooling also, together with the aerosol particles. Then the interaction of the aerosol particles with clouds is very important for us to study, understand to develop the models now for climate purpose. Now, as we can see in this slide, the uncertainties associated with the greenhouse gases now are not fairly understood, the effect of those greenhouse gases, whereas the aerosol direct effect due to scattering absorption are also understood to some extent, whereas the aerosol indirect effect, that is their interaction with the clouds, the understanding is very low as of today. So that is why the importance of interaction between the aerosols and then clouds, the role of the condensation is important now to study by making use of the remote sensing purpose. Now, what is required for reducing the uncertainties in modeling? Quantify aerosol cloud radiation interactions so that they may be included correctly in the climate and numerical weather forecasting models to provide. So for that purpose, we require to get the vertical profiles of natural and anthropogenic aerosols on a global scale, their radiative properties and interaction with the clouds. So to derive that, we need to have vertical distribution of atmospheric liquid water and ice also on a global scale, their transport by clouds and radiative impact. So actually the study of the atmosphere consists of many processes simultaneously happening. So we'll be able to, but the aerosols and the clouds, they play a major role. So if you are able to study and then put them in the model, it's possible that can reduce uncertainties connected with the modeling there. Now, as I said, the aerosol particles, they block the direct cooling by blocking the sunlight, and they absorb the, due to like carbon aerosols and all, they lead to heating. So can we quantify these direct aerosol effects? Then that is the question there. Then similarly, aerosol clouds, aerosols act as a cloud condensation nuclei. More aerosols lead to more reflective cloud and less precipitation. So that is why the precipitation characteristics of the clouds are modified because of the interaction of the aerosol particles with that. Now, clouds, radiation, and climate, more clouds reflecting sunlight, they are back to the space, so you have a cooling effect, and more high altitude clouds, they are less IR to space, so warming. So cloud feedbacks dominate the sensitivity of climate to external forcing, but existing models do not even agree on their sign. Whether it is positive or negative is not clearly known. That means whether cooling or warming is not fully measured, quantified. Do current models have the correct vertical structure, overlap, amount of condensation, sedimentation rate of ice, etc.? These models are really taking care of these properties of the clouds. Then convection and precipitation. Convective precipitation is produced by subgrid scale vertical motions of cloud condensate. Passive satellite observation suggests 0.5% of convection penetrates cold trap into the stratosphere. So are these parameterized motions correct? So you want to put it in the model. How much moisture does convection introduce into the stratosphere? So these are some of the questions what we require to study and then quantify these effects of aerosols and clouds. So one has to look into the system of capable of assigning height to the distinct features observed with the ability for working even in the absence of naturally available radiative sources, essentially sun. So most of the systems now are able to give us the total integrated value of the effect of these clouds or aerosol particles, but there is no way of finding out what is happening where, at what altitude the particular aerosols are whether cooling or warming up. So that kind of information is not available with the present methods. As such, there is a growing interest in active techniques such as Lidar and synthetic aperture radar, promising essential advantages compared to the well-established satellite-borne sensor systems. So the satellite-borne systems are today, before the radar systems in space, we had many passive systems which are able to give us this information only on an integrated way. That means from sun to atmosphere, ground total atmosphere values of the clouds or aerosol particles. So whereas Lidar is unique in the sense that it is providing us the range information also. That means you are able to resolve the information what you measure in terms of the altitude of coverage. So the laser remote sensing device, which finds wide use in these applications. The range and kind of applications are today are very high, making use of radar system. Now one has to look into the systems capable of assigning height to the distinct features observed with the ability of working even in the absence of sun. That means in the passive systems work on the sun solar radiation as a source, whereas with a Lidar system we have the active radiation in our hands. We can control the wavelength, we can control the polarization, its intensity. So these things can be wavelengths, and we can control this radiative source what we are using in the Lidar system here. Now, measurements of parameters important in evaluating the composition, structure, properties, and dynamical behavior of the atmosphere have been successfully undertaken using the radar systems there. In future, radar systems could play a key role in predicting weather by providing the pertinent basic information on a global scale. So another thing is the greenhouse gases, trace constituents of the atmosphere, are of great importance in Earth radiative budget. The determination of sources and sinks of minor species and their residence time will be beneficial also to climatology. Lidars are able to suitable for determination of the concentration profiles. That is more important now, because the profiles in terms of height information will be provided for many of the trace constituents like ozone, water vapor, methane, etc. with high precision. Now, characterization of aerosols for their optical properties, spatial and temporal variabilities with high vertical resolutions is very much needed in the radiative budget estimates. Anthropogenic, that means man-made aerosol particles due to human activities, play an important role in the climate behavior. Lidar provides important observation data on urban particulate emissions from space on a global scale. Lidar systems are very useful for environmental monitoring and air quality measurements. Lidar techniques complement the existing measurements and greatly extend the studies undertaken on ocean and rivers also. Detection of vegetation characteristics, tree height canopy over large forested areas are other important applications of Lidar in other areas there. Now, we have a Lidar system at ground, but then still what you measure is only applicable to only a small region or localized measurements there. So suppose you would like to have a global modeling, it is required for us to have space-based measurements also. So space technology has opened new possibilities of observing the Earth and Earth atmosphere from outside, stimulating the development of remote sensing techniques. The use of spaceborne instruments to measure atmospheric parameters like cloud cover, water vapor content, aerosol optical depth, temperature, etc. is quite well established now. Also, presently, a number of important operational applications, both on land and oceans, are using passive sensors. Now, the satellite systems are earlier have been using the passive systems where they use the solar radiation as the source for making the observations there. However, as I said earlier, all these measurements will give us an integrated value, but not the range resolved values there. Now, specifically what you require to measure from space for global measurement, environmental climatological research, then operational meteorology, the data will be of direct help to weather forecasting models, whether mesoscale, region, or global. The data will be particularly useful at night over the sea, where observations are very scarce. Now, let us see what is this basics of remote sensing. My talk will be, I think, more useful basically for the students because these are all known to the experts here. But still, I would like to cover. Remote sensing is any technique for measuring or observing or monitoring a process or item without physically touching the item under observations. That means from a stand-up distance, you are able to make the measurements with the remote sensing. There are two classes of remote sensors. One is the passive remote sensor and then active remote sensors. Passive remote sensing do not include the energy source on which the measurement is based. So examples of passive remote sensing include eye and optical telescopes, where they make use of the background radiation as the source for measurement. Now, active remote sensing includes energy source on which the measurements are based. Radar is a widely known form of active remote sensing. In radar, the instrument emits a radio wave and senses the radiant energy, which is reflected from the target. Since the speed of light is known and the time delay between the emission and return is measured, the distance to the target can be determined by the radar. Now, in the place of a lidar, lidar is similar to radar. So, what is lidar? Lidar is an acronym which stands for light detection and ranging. So, it tells us that you are able to measure the detection of the light as well as simultaneously the range information also obtained like in a radar. So a radar transmits a laser source into the atmosphere and then you get back the scattered or reflected from the atmosphere. So you could see that the detector there, it measures the intensity what is received due to scattering or absorption by the atmosphere. So as you go up in the atmosphere, the number of particles or aerosol particles number density is coming down as well as size of the particles also come down. So because of that, the scattered signal what you get is coming down as you go up. Similarly, the clouds, they are nothing but a composition of some more aerosols there. So you have got a lot more signal from the clouds itself. So the signal what we are showing there here, you can see there is an increase all of a sudden at the higher altitudes. On the x-axis, I am plotting the signal intensity, and the y-axis is the altitude. So as you go up, the signal is the return signal from the atmosphere is coming down, and then there is an increase all of a sudden due to the cloud in the at particular altitude there. Okay, so here basically the lidar, when you try to use it, so you have the laser transmitter, you have a pulse which is being sent into the atmosphere, and then unlike a radar, the atmosphere is as a target scatters all over. That means you have a lidar working in the area of volume where they consist of distributed scatters there. So unlike a radar where you have only single target or multiple targets, they are reflective targets. Here, right from the ground itself, you have the aerosol particles and gas molecules, a composition of two-component atmosphere there. So you have got a continuous signal, unlike in a radar there. Next slide. So radar techniques are based on actions, namely scattering and absorption. As you send the laser towards the atmosphere, two processes can occur, only scattering and absorption. In absorption, you can make use of scattering or absorption. In absorption methods, observations are made at the wavelength of the incident radiation in the absorption lines or bands characteristics of a particular gas there. Scattering is the process by which a particle in the path of an electromagnetic wave continuously extracts energy from the incident wave and re-radiates the energy in all directions. So here the scattering happens, and then once the photon touches the aerosol particle or gas molecule, you have the scattering all over, and then, but you will not be able to measure the total scattering intensity. So the instrumentation part of it, we keep the receiver so that you measure only scattering intensity which is coming towards the transmitter. That means 180-degree scattering, which we call as backscattering. So in all lidar measurements, we basically measure the backscattering signal and then try to characterize here. Similar to radar, a laser light pulse is sent to the atmosphere and is used to, as a spectroscope probe of the physical state and chemical composition of the atmosphere. So the emitted laser beam interacts with the aerosol particles or clouds or any other molecules, and then you have this change in the intensity, polarization, and wavelength of the backscattered light. So any of these things can happen. Sometimes you change only intensity, sometimes only change of polarization, or sometimes we change of wavelength here, depending upon the scattering mechanism, what you are going to use it. So in terms, sometimes all three can happen also. Now the distance, as a lidar, like a radar, the distance to the scattering medium can be deduced with high accuracy from the time delay of the return signal. As the laser is pulsed, the method allows a range result measurements to obtain a vertical profile of the parameter being studied. Lidar systems are used in the wavelength range starting from ultraviolet to IR by using different types of lasers. Lidar techniques are based primarily on the interaction to backscatter and the absorption there. Now, based on the interactions, what different types of interactions, we have the lidar systems, which can be named as the Rayleigh scattering, Mie scattering, resonance scattering, fluorescence, Raman scattering, absorption. So the absorption is the second interaction there. So in the scattering itself, we have different types of scattering mechanisms. Rayleigh scattering is applicable to the when the scatter size, that means the aerosol size or molecule size, if it is depending upon the size of that. We have the Rayleigh scattering when the scatter size is much smaller than the wavelength of light. In the Mie scattering, when the size of the scatter is larger or comparable to the probing wavelength, we call it the Mie scattering regime. Resonance scattering, excitation, with a excitation with laser produces emission photon the same wavelength. So this is applicable for measurement of atomic species in the mesosphere, like potassium and then sodium, lithium. So these are also important as far as the atmosphere is concerned. So making use of different scattering mechanisms, we do that one. Then based on the mechanism what we are using, we can classify the lidars into Rayleigh lidar, then Mie lidar or aerosol lidar, Doppler lidar, or measurement of winds in the atmosphere, fluorescence lidar for the measurement of some of the atomic species in the atmosphere, and differential absorption lidar is another technique which is used for measurement of the concentration of many chemical substances like or pollutants in the atmosphere. The Raman lidar also is used for measurement of atmospheric constituents like ozone or pollutants like SO2 or NOx. And the resonance lidar is basically used for the measurement of the atomic species in the upper atmosphere like potassium and sodium. So different types of lidars are used for different applications now, different studies what you would like to have. Now let us see what is the basics of lidar equation. So here, as I said, we are trying to measure, or we are measuring the scatter intensity, what is being received by the receiver at the ground station here. So the received signal can be calculated PR is the power received at the ground. is proportional, is equal to P0, the transmitted laser power, C tau by 2, velocity of light, tau is the pulse width of the laser, and K is the radar constant, and beta is the backscatter coefficient to the atmosphere, and then R is the range, A is the area of the receiver, and alpha is the extinction coefficient to the atmosphere. Now, in the radar equation, you can see that the signal what you are going to get back is proportional to the power what you are transmitting from the laser, and also the other system constant. If you leave, then you have got the two terms there, beta and alpha. One is the backscatter coefficient, which is scattered from the by the scatterer towards the, that is back 180-degree scattering, and alpha is the extinction coefficient of the atmosphere. So now you could see that when the beam is traveling with the atmosphere, because of the scattering, some of the light is coming back to the ground at 180-degree scattering. The rest is now going as a loss to the actual ongoing transmission. So in other words, alpha is the total extinction, whereas beta is the part of the scattering which is being measured by us because of the instrumentation convenience there. So the alpha and beta are related because alpha is the total attenuation, whereas beta is a part of the attenuation which is being received by us. Now we measure only the beta, the backscatter coefficient in the radar measurement, and then alpha is not known to us, but they are related. So in other words, there are two unknowns, alpha and beta. One is the total attenuation, another is the backscatter intensity which is coming back towards the transmitter there. So by making it so, you are measuring only the intensity, backscatter intensity only you are measuring, but you are trying to derive two unknowns, alpha and beta here. So they are related, the relationship is not known to us, which varies with altitude. So there comes the problem of resolving or inverting the radar signal for making the measurements here. So we could see that actually what we are interested is the attenuation caused by the atmosphere for the incoming solar radiation, and then we are simulating that by having an active system and having a known wavelength, known power to us, and measure the backscatter signal there. So we have to derive the values of beta and alpha from the measurement of beta, what you have done here. So there are various techniques and different groups. You make use of different methodologies to derive the values of extinction and other things. Now, similarly, we have the Raman technique, where the greatest potential for measurement of atmospheric gases like water vapor, temperature. The basic requirement of transmitter is that the wavelength should take advantage of the inverse port power of dependence of the cross section, because 1 over lambda to the power of 4 is the when you increase the lambda, then the intensity comes down. So you try to go down to lower wavelengths to make use of Raman signal, Raman measurement. So, and also we require to have high energy and pulse repetition rate should also be available. The receiver needs to incorporate spectrometer for interference filter matched to the Raman shifted wavelength. So here we measure the Raman shifted wavelength for a particular molecule, and then similar to the Lidar equation, make use of the same Lidar equation to measure the intensity of backscatter signal from the Raman measurement. And then the comparison with a nitrogen Raman will be able to, or oxygen Raman will be able to quantify the water vapor mixing ratio, which is a very important parameter for the meteorology people. So Raman radar is used for measurement of many of the minor constituents in the atmosphere and also some of the pollutants in the atmosphere. The advantage of the Raman technique is that you need to have only one laser source for measurement of many constituents like minor species in the atmosphere. Next slide. Now, Raman radar is used for measurement of a number of atmospheric molecules and pollutants. The magnitude of the Raman shift is specific to the excited molecule, and the amount of detected light is proportional with the molecular atmospheric concentration. So what you should know is that what is expected, what is known, the Raman already available to us. So suppose you would like to measure water vapor, we know that if we transmit at 532 nanometers, you are getting back the scattered signal at 607 nanometers. So then you have the measurement of the intensity at that wavelength by making use of suitable receiver there, and then filtering out the background or other radiations there. And then based on the method of analysis, Raman radar technique can be classified as vibrational Raman method or rotational Raman. You can use any of these two methods, either vibrational Raman or rotational Raman here. Now you can see the spectrum when you have the Raman spectrum. You have the vibrational Raman. For example, if you transmit at 532 NDR laser, we have the O2 shifted at 580 nanometers, whereas the N2 nitrogen at 607 nanometers, similarly water vapor at 660 nanometers. So by making use of one laser transmitter at 530 nanometers, you can simultaneously measure many of these minor constituents or pollutants in the atmosphere. Now, we have the pure rotational Raman also, which is very close to the transmitted wavelength of 532 nanometers. It is shifted to the lower side, but then this is the intensity of the pure rotational Raman is very high compared to the vibrational Raman. So one can make use of the pure rotation also, but the only problem is that the wavelength shift is so small, you require really very good filtering to measure the shift happening in case of pure rotational Raman. But the advantage is that you have the higher intensity coming from the molecule there. But then you can make use of that pure rotation Raman for the measurement of temperature in the atmosphere, whereas the vibration Raman, we make use of the measurement of concentration of many of the molecules in the atmosphere. So because the pure rotation Raman, if you see the envelope of the pure rotation Raman, it is slowly varying. So you can concentrate the measurement of intensity at two points in the received signal, and then you can take the ratio of that, and then you can get back the temperature profile in the atmosphere by making use of the pure rotation Raman spectrum. So the Raman backscatter radiation dictated by the radar is described by the radar equation. So received power at Raman is consists of the PR is the Raman signal, C the radar constant, and then the combined aerosol, because when you transmit the laser beam at 532 nanometers, you have the return signal due to elastic scattering from the Rayleigh and Mie scattering from the aerosol particles and neutral atmosphere, and simultaneously you have the Raman signal coming at the shifted line. So the first term in the exponential term describes the extinction of the laser beam at laser wavelengths going up towards the target, and when the return signal due to scattering, the second term describes the extinction due to backscatter towards Raman plus our other Rayleigh and Mie also. So this is the total signal you get here. So you will have to see that because the Rayleigh and Mie signals are very high intensity, because the cross section of Raman scattering is almost like 4 orders lower than the Rayleigh scattering, whereas Mie scattering is about 10 times larger than the Rayleigh scattering. So you have a very background noise signals both from the Rayleigh and Mie, which you have to take out from the received signal and then measure the Raman signal. So there the instrumentation part of it really tough here to filter out the Rayleigh scattering, Mie scattering at the same wavelength, whereas the Raman scattering at the shifted wavelength there. Raman radars have the distinct advantage of providing profiles of water vapor in the same atmosphere volume of the aerosol measurements. So simultaneously, you can measure the aerosol profile as well as the water vapor profile, and then the interaction of aerosol with water vapor can also be studied by proper instrumentation, where you filter out when you measure the Raman signal, you have to filter out the other scattering mechanisms there. Now, the aerosol extinction measurement, Raman nitrogen signal can be used for aerosol extinction measurement. Also, because anyway, for aerosol measurement, you can use any wavelength. Similarly, Mie scattering also you can use any wavelength. Only thing, the cross sections are quite high here. Now, the aerosol extinction corresponds to Raman signal. So you can obtain by measurement of the Raman signal and then the background molecule, and then you can get back the ratio of the scaling of aerosol extinction for 2 wavelengths at 532 transmitter wavelength, and the received Raman signal at 607 nanometers from the nitrogen. So we'll be able to measure the aerosol extinction from the Raman measurement also. Now, as I said, the pure rotation Raman spectrum of molecular nitrogen can be used for temperature profiling of the atmosphere. So the temperature is deduced from the intensity ratio of 2 parts of the 2 bands, the nitrogen rotational Raman signal. The method relies on taking the ratio of the pure rotation Raman spectrum atmospheric nitrogen at 530 and 529 nanometers. They are close, very close, because the excitation wavelength is 530 nanometers. But whereas the pure rotation Raman, you have a band where it is continuously coming back with the 530 to 520. Then you can take the ratio of these two and then try to, for calibration purpose, you can get back the alpha and beta values there. So this is the advantage of the pure rotational signal is about 10 times higher. So measurement is easier, but filtering is problem there. So you need to have instrumentation proper for measurement of the signal as well as eliminating the background there. As the wavelength difference between the elastic and rotational Raman difference signal can be neglected, assumptions for the wavelength dependency of the aerosol extinction coefficient are no longer necessary there. So that's why we make use of the pure rotation Raman for getting the temperature profile in the atmosphere and also water vapor. Next slide. Now, another important interaction of the laser with the atmosphere is the absorption measurement. So earlier, we have seen different types of scattering mechanisms that are used for different measurements, both aerosol and minor species in the atmosphere. Now, the absorption is the most sensitive method. So you measure here, basically you measure the absorption caused by a particular gas, a pollutant or natural gas in the neutral gas in the atmosphere, and thereby you'll be able to reduce the concentration of the particular gas, species in the atmosphere. So now the absorption caused by a pollutant, thereby its concentration can also be obtained here. Now the dial method here, next slide. So here the normal absorption method where you have a laser source and then you have an optical receiver. Suppose you would like to measure the concentration of any gas or a pollutant in the atmosphere, you can transmit a laser of known power and then you have a receiver and then you measure and then how much it is reduced due to extinction by the gas can be obtained, and thereby you can find out the concentration of, once you know the absorption coefficient of particular gas there, you can find out the concentration of particular gas in the atmosphere. It can be used for pollutants there. Similarly, so in it can be two configurations here. One can directly you can receive at the other end, or you can put the receiver close to the transmitter also by having retroreflector. So where it is passing the two-way, that means it's going to the retroreflector and coming back. So it is traveling 2 times through the actual volume here, the atmospheric gases there. So it is sensitivity is more, but also instrumentation part of it is convenient also to have this kind of configuration as a B here. Next slide. Now the most important here, as you see that earlier system, it measures the total integrated value of in the path here. So you do not know exactly, suppose you measure 1 kilometer total path and find out the concentration. You do not know exactly what is the concentration level, different distances there. Whereas one would be interested really when you want to measure or to follow the pollutant in the atmosphere, you would like to know the concentration profile in terms of range also. So we make use of the most powerful method in the absorption technique, what is called differential absorption technique, dial technique, where you transmit the, you have a tunable laser. Here you require a tunable laser. So initially you transmit the laser at, in the right side, we are seeing the absorption spectra of particular gas, what you would like to measure. And you find the absorption at 1 lambda on line, 1 lambda, it is maximum absorption. And we have to if you take the alpha off, sigma lambda off, it is the off the absorption band. So that means you select the 2 lines, one falling on the absorption band of the particular gas, and one outside or at least lower than the absorption from at the other wavelength there. So you have now the same signal is scattering signal like Rayleigh or me is measured back from the aerosol particles, whereas the gas is pollutant gas is present in the atmosphere. Now, when you transmit at lambda on, it is now the return signal is absorbed, the scattered signal is absorbed, contributed from the absorption, reduced by the absorption due to the gas there. Whereas when it is offline, when it is not in the absorption or less absorption, what you get back scattered from the aerosol particles is now little increase because of the less absorption there. So you can see the power received now, lambda off is higher in the signal what you get with range is that groove. You got a better signal there, more signal, whereas the lambda on, it is more absorbed, so you have a red one. So you can see the difference between the return signal at the 2 wavelengths is increasing as you go farther and farther. So the way I said this is a more powerful technique in the sense that even though the range is increasing, the sensitivity of the system is increasing here because the difference in the absorption caused by the gas at the 2 wavelength is increasing. So it is a very powerful method which is used for measurement of the pollutant in the atmosphere or natural gases in the atmosphere in terms of with a range resolved measurement. That means you can say that every 100 meters, what is the concentration? Suppose you measure up to 2 kilometers, you can say that 100 meters, this is the concentration, 200 meters, like that, you get a profile there. So here you can derive the concentration at a particular range by making measurement at 2 wavelengths, and also received power at the PR and P off, and also you will be requiring to know about the absorption coefficient of the gas at the two wavelengths. So once we have that information, you'll be able to calculate the concentration of the particular molecule at that range there. So here it shows the actual signal, how do you receive. So return signal, you can see how it is changing due to absorption between the two lines, P off and P on. And you take the ratio of the received power at the two wavelengths, and then log ratio and the differential of that. So it will give you the actually the concentration of the particular gas at the range R1 to R2. That range bin, you'll be able to measure the concentration there. Now, this is the, already I have shown that one. So they received the concentration of particular gas at the range R can be derived by measurement of the power received at the P on, the online wavelength, and then offline wavelength. And then after knowing the sigma on, sigma of the absorption coefficient, and C tau, tau is the pulse width, see the rush of light. So from that, you'll be able to get the concentration profile. One is used for measurement of many pollutants, such as ozone, carbon, CO6, or OH, OCS. So most of the pollutants, but only thing is the requirement here is that you need to have a laser. Specifically, if you want to measure a particular gas, you require to know what is absorption spectrum of particular gas, and also you require two wavelengths, and then falling in the absorption, one of them it should fall in the absorption band of the particular gas there. One should be outside, or it can be another part of that spectrum also, with a lower absorption coefficient there. So that is the requirement. That means for each of the molecule, you require a pair of lines, a pair of wavelengths corresponding to the absorption spectrum of the particular gas here. Whereas in the Raman lidar, you can make use of any laser. Only thing is, depending upon the particular gas, you have a Raman shift. So you can simultaneously measure many pollutants, many gases using the Raman lidar. Whereas the differential absorption technique, you require to have two lines, pair of lines for each of the molecule there. So that's the disadvantage. But at the same time, the range to be covered is quite high here, because you are basically using the mist scattering, the background aerosol scattering you are using for characterizing the gas there. So indirect way of using the mist scattering for the measurement of the absorption caused by the gas there. So it is more sensitive, and you can cover long range also here. Whereas in the case of Raman lidar, the cross sections are being very low, so you'll be able to cover only a few kilometers. Unlike the dial lidar, where it can go even up to tens of kilometers in the atmosphere there. Next slide. So this is the typical simulation lidar signal, making use of the actual system what we have. We try to simulate the SO2, NO2, O3. So what is making use of the, so the lower the wavelength, you have boson, for example, absorption band at 266 and 299.5 nanometers. You have a wide absorption band for the ozone. So we make use of the online, offline within the absorption band itself, where it is more absorption at 266 nanometers and less absorption at 299.5. So you can make use of the two pair of lines, the two lines as a pair, and then measure it. So one can make use of measurement of many pollutants in the atmosphere by making use of differential absorption Raman lidar in an industrial location also. One can use it. And also you can see how the pollutant get dispersed. So we can continuously real time, you'll be able to measure the concentration and how, in which direction the pollutant is spreading, and also how it is getting dispersed in the atmosphere. Can be real time, you will be able to measure here. So this is very useful for industrial locations where you would like to continuously monitor the spread of the pollutants which are anyway being emitted from the source. You can measure at the source level what is the concentration being emitted, and then how it is getting dispersed in time with the distance. So it is possible that kind of measurements there. Now the other application of this lidar in the imaging lidar, where it is used for a surveillance purpose, mainly for across the border. We have developed one system where you can use for night vision applications, where you have a laser working in the infrared region. So you illuminate the laser with the in the IR, and then you have a imaging, and then you can scan over the around the 360 degrees around the azimuth, and then get a continuous measurement of the any border movement or any vehicle or any human movement across the border. This we have supplied to one system to Army also. So next slide. So this is the system where it is mounted, the laboratory system right now here. So you can see that other transmitter there. Next slide. So some of the night observations, you can see a distance of 420 meters from car. This is raw image. Now what we do is that we do some signal processing also, then improve the contrast of the actual image what is being obtained. This is complete dark conditions. We are able to see up to I think 1 kilometer or 1.5 kilometers, making use of by increasing the laser power, you can still able to see further also. So now another important project what we had what we did was the measurement of what is called the turbulence in the atmosphere. This is required for target location for example, missile applications. We would like to know what is the effect of the atmosphere when the beam is propagating through the atmosphere up to a large distance like 5 kilometers and all. Because before reaching the target, the beam gets altered by the atmospheric turbulence in terms of its temperature ADs in the because of change in refractive index across the beam. So we'll be able to characterize the model atmosphere. So what is called the refractive index structure parameter CN square can be measured by making use of a radar. You will be able to get a profile of the till the target here. So you know that CN square varies with both time, day and night. It varies, and also with the daytime itself. Morning the CN square value is different. By evening it will be different because depending upon the depth emission after the heat getting heated up. So one would be interested in this parameter CN square. So we have a project to measure the CN square profile, which is coming because of the atmospheric turbulence. Yeah, next slide. So this is actually the variation of CN square between day and night. So a lot of variation happens between the day and night also. So that's what we require a model to be generated mainly for the target designation purpose. Now, in the technology point of view, so there is a requirement in the country now to have a number of the earlier later we'll be seeing that the initial lidar systems what had been developed, they occupy a large space, almost like a laboratory. And then because the large laser systems, cooling systems, what you require, and telescope. So because of the technology at that time, so there is no way of having a different cost also is very high. So one would be able to locate a single station and then conduct the observations which are pertinent only to particular location there. So it is possible that you can have a compact lidar system which can be taken to different locations also. So in the country we have a requirement of a large number of compact aerosol lidars for measurement of clouds and aerosols in the atmosphere, which is the requirement is that they will be basically interested in characterizing the clouds, the cloud cover across the airports for aviation purpose, and similarly for the IMD for weather forecast, they require a continuous operation of the compact lidar at different locations there. So Ananth Technology has got a contract to develop the what is called celometer, celometer is nothing but a lidar for measurement of cloud. So we call it as a celometer. So this is a very compact system, but it has to withstand the complete environmental conditions and unattended operation is required. So we have developed this lidar for DRDO purpose. Actually, they are going to supply to different locations there. So it comes next slide. So it consists of again a transmitter, laser transmitter, and then working in the infrared, and then we have receiver. So you can see that how it is so compact now. So it I think it weighs about I think 35 to 40 kilograms, and it can be taken transportable to different locations. And they are planning to install this at different airports to continuously monitor the cloud cover, because for landing time the aircraft people require the cloud content before landing, the visibility as well as the cloud cover. So that information is obtained on throughout 24 hours by making use of a system that has been developed now. Next slide. So then we have a program now with JNTU. We have started a research program to measure the coronavirus by making use of the laser-induced fluorescence. So laser-induced fluorescence is very well known and is used for many other applications, including bacteria identification also. But then the work on the coronavirus detection, mainly virus detection, is not very much already proven. So we are making use of the laser-induced fluorescence. It is possible that we would like to make use of a UV source for 266 nanometers with a 5 kilohertz PRF, 250 milliwatt average power. So this will be used for pumping the illuminating the target with this laser, UV laser, and you get the fluorescence spectra, and then you have the information about the fluorescence spectra in a priori. You'll be able to identify the actual virus and then quantify the virus content also from a stand-up distance. The main advantage is that you need not reach the actual target, but from a distance, you'll be able to measure the. So this is only still in the initial stages of development. Next slide. So it consists of laser UV source and then exciting radiation, and then we have a sample now. The virus sample is put in a cuvette there. So you have the fluorescence spectra and measure the record the fluorescence spectra along with the other scattering. You have to filter out the other laser wavelength itself, because 260 we have to filter out and then get the fluorescence spectra. From the fluorescence peak as well as the fluorescence yield, it is possible to identify the virus detection of the virus there, and also if there are other virus present also you'll be able to simultaneously see. But then still this is only a proposal startup now, so we would like to see whether how far we'll be able to develop this one. Now the importance of real-time studies on aerosols and clouds. Now there is a program sometime back, many people have attempted this, what is called the cloud seeding for actually creating the improving the rainfall at different locations. This has been attempted by different laboratories in the country. Earlier, IITM and even JNT also has attempted. Some of the experiments have been done by seeding the cloud with any aerosol particle, so that you will increase the precipitation. So thereby you will be able to get a rainfall at a particular location. Not that you are creating the clouds, but already the cloud should have the moisture in them. But you introduce another aerosol material, any chemical, or it is given like that. So once you have that kind of thing, then the precipitation, the cloud aerosol become heavy, and then they give rise to the precipitation. So you'll be able to increase the precipitation by making use of introducing a seeding material in the clouds. So this is now, but then the program was not very successful in. So people have abandoned that program because it is not reliable. But then the reliability of that cloud seeding is now can be ensured if you are able to measure in real time the aerosol content and in the cloud and the interaction of the aerosol with the cloud moisture. If you can really see that, then you will be able to make out whether the precipitation can be still increased or not, what is the size of the seeding material required, and what is the density of the seeding material. So those things are still not known, because people have been doing it randomly without much of observational facilities there. So what we proposed for this one is to make use of the radar and lidar. To simultaneously, radar will detect the actual cloud where it is located, and lidar will give us the time of our exact seeding there. So this is a program now. It was proposed by, it was accepted by Kerala government also for, they have allotted 10 crores for this program, cloud seeding program. But then after that, immediately within a, before we started that program there, so there was a very, very heavy rainfall all over. So, so that is why that program did not take off. But now today there is a currently UAV. They have got a regular program on cloud seeding, making use of the seeding with an aircraft, some of the clouds, which they are getting very good results now. But then we sent a proposal there that whatever you are doing, it has to be real-time measurement is required on the clouds, and then the also the aerosol content or the properties of the aerosol content in the cloud are to be monitored before you really decide at what time you are supposed to seed the material and what is the chemical composition, size distribution of those aerosol particles, what you are going to seed. So that's what we sent a proposal to UAV also. It is being under consideration now. That is a big program. They have been giving the program for different all over global level. They are doing this program, but it was not yet accepted. Okay, this is only the sort of proposal at the time. So what you require is to know about the cloud properties by making use of a polarization measurement. When you send it towards the And then what is the depolarization happening due to the cloud aerosol particles? Then also you make to simultaneously measure the size distribution of the aerosol particles around the cloud here. So that kind of information is required really to make the program successful, and then increase the precipitation from a water-bearing cloud, a moisture-bearing cloud. It is possible that, so some of the seeding materials like silver iodide, dry ice, calcium chloride, they have tried, and then to some extent it was successful, but it is not reliable, and it was found that it was not reliable. So then we said that unless you real-time monitor the cloud properties and also the water content of the clouds, you will not be able to 100% make sure that it will give higher and more precipitation there. Next slide. So this is what about, okay, I don't want to go more on this one. So what we propose is making use of a multi-wavelength radar will be able to characterize the cloud in real time, and then try to find out exact time of seeding as well as the material to be seeded there. So that kind of information, still it is a research program, but not yet proven practical consultation there. Now the coming back to the Lidar, what is instrumentation part of it? So what is the, we know that the difference for this is the basics of Lidar. So why we require earlier, as I said, people have been using the white light source, and then the laser, with the advent of laser, we have found out a lot of advantages. So make use of different types of laser sources. As I said that earlier, that you have different mechanisms like different scattering mechanisms and then absorption technique. So they require different wavelengths now to be as a probing wavelength for remote sensing purpose. Next slide. So we have made use of the radar systems are today make use of many laser sources like NDR, and then its harmonics wavelengths, and then excimer lasers in the UV and CO2 laser, tunable diode laser, DF laser. So all of them are, because you know that some of the techniques like Raman Lidar requires a more powerful laser, and wavelength is not much of importance there, whereas fluorescence required, induced fluorescence required UV lasers. Next slide. So like that, now today we have the Lidar systems making use of the laser sources from the UV visible and also in the infrared sources for different applications, making use of different techniques there. Next slide. So some of the properties which are required to be satisfied when you want to have a Lidar system, the laser parameters are important, like peak wavelengths. What is the peak wavelength? The spectral line width, because in terms of differential absorption, you require to know the absorption coefficient of a particular line, online or offline. So you have to spectral line of the transmitted width is required, spatial distribution of energy, and the divergence of the laser, then the pulse width of the laser, repetition rate, efficiency of conversion from electrical to optical, then output power, then suitability for field use. Some of these parameters are important for when you want to design a radar system for remote sensing purpose. So this actually summarizes the different techniques, what I have mentioned earlier, the Me Lidar, Dial Lidar, Raman Lidar, for different measurements in the atmosphere. So here you can see that the elastic scattering, where there is no change of wavelength, Me Lidar and Rayleigh Lidar, and Raman Lidar, inelastic scattering, where is a shift in the wavelength, what is due to Raman scattering. So we make use of for measurement of various species in the atmosphere or pollutants. Similarly, resonance fluorescence for measurement of the upper atmosphere, some of the atomic species, Doppler for wind measurement, induced fluorescence for organic motion, that hydrosphere radar, and similarly, a laser altimeter for measurement of topography at surface is possible to make use of a laser altimeter. Next slide. So then the evolution of the radar systems now, to start with, as I said, they have become very long, I mean, in terms of cost, in terms of size. So they are unmanageable in the sense that they have to be mounted in a housed in a laboratory or in a truck, so that we can take it to different locations. So later on, we have the different techniques have come up, like differential absorption technique, and then also the advancements in the laser technology, and then in terms of optical receivers and also optical detectors and signal processing. So they contributed a lot of change in the instrumentation part of the Lidar systems. So you have today very compact systems all over, which can be used for measurement of various parameters simultaneously. Next slide. Okay, run through quickly. Yeah. So now so here you can see that just to show that the initial lidar systems are so large in size, they have to be put in a truck here. Total laboratory is now put in a, so that kind of, this was somewhere in 80s what was developed for a transportable lidar system. Next slide. So this is a second generation lidar where we make use of Nd:YAG laser in the 532 nanometers being transmitted there. It's a multi-wavelength lidar system, second generation one. And next slide, clear on through. So here later, as I said, that we had one program supported by DST in one of the engineering colleges here. So we developed a still a little compact now. So this system is able to measure the atmosphere up to 22 kilometers. So with a very compact system, which can be easily transportable to anywhere location. So this is what was developed now at that time. So this is being used now for studies on the aerosols and clouds at that location. Next slide. Okay, there's some of the subsystems of that lidar was developed for. So now this system, what we propose here, this is a what is called a M3 lidar, where is a multifunctional, multi-wavelengths, and then you can make use of for different applications here. So this is a sort of test bed sort of thing where you have Nd:YAG laser pumping a dye laser, so that is tunable. For differential absorption measurement, you require a different pair of lines. So then you have transmitting to the atmosphere Nd:YAG or dye beam simultaneously, or one after another. You can do that. Then we have receiver 500 millimeter large telescope. Then after you receive backscattered signal, is now you can simultaneously measure. Here there are 3 channels for measurement, making use of a beam splitter there. So any 2 channels can be simultaneously used for measurement of the, for example, you would like to measure the Raman signal as well as the Rayleigh signal. It is possible to simultaneously measure by making use of the photomultiplier at the PM1, PM2, PM3, PMT photomultiplier tubes there. So the received signal, as we have seen that earlier, the backscatter coefficient and then the extinction coefficient values, you can see that the received signal is almost 10 times lower than what is being transmitted. So suppose you transmit a 1 watt laser power into the atmosphere, so what you get is almost like 1 nanowatt. So you have to measure very low light levels from the scattering, backscattering. So you require to make use of different types of detectors corresponding to different wavelengths, because photomultiplier tubes are wavelength sensitive. So depending upon the laser wavelength, you have to make use of different photomultiplier tubes. At the same time, when you go into the infrared region, you require to, you cannot use photomultiplier tubes, but you have to go for avalanche photodiodes, which are sensitive in the infrared region. So for some of the applications, we make use of the APDs also. For example, the cloud lidar, what we have shown, the transmitter is at 1064 nanometers. So you cannot use a photomultiplier tube for that to measure the low sensitivity. So we go for a APT system. Now the system what we are showing here is the photomultiplier tube output in the lower atmosphere contains more of aerosol, large number of large size and more number in the lower atmosphere. So naturally the backscatter signal is going to be large relatively compared to the higher altitudes. So your signal processing in such a way that lower altitude measurement is done by a photomultiplier tube, which is more sensitive with better amplification, whereas in the upper atmosphere, the same pulse when it's traveling, simultaneously you get the signal from all the altitudes, because as the beam is transmitting, going into the atmosphere, you have the scattered signal coming from different altitudes. So you need to measure the signal levels, which is dynamically varying, almost like 7 to 8 orders. So your detector system should be able to see that the measurement is done both from the ground level to your 20 kilometers to altitude. So towards that, you require different types of detectors, and also the instrumentation requires that you have to, for example, you want to measure at daytime, you require to filter out the background noise. So you have to have sort of a very good filtering technique. So that this system has got that kind of photon counter. When you want to measure at higher altitudes, you need to measure the individual photons as a photon counter. On the other hand, when the signal is strong in the lower altitudes, the output of the photomultiplier tube will be in the analog mode. You can in the current mode, so you can detect the signal easily there against the background there. So your total system now, the instrumentation part of it is in terms of transmitter, in terms of the receiver, and in terms of signal detection and processing. So you have to have that kind of a system where this can be used for measurement of various parameters in the atmosphere using different wavelengths and different lasers there. Next slide. So this is some typical signal what we received from the other lidar system, portable lidar system. Next slide. So some of the results what were obtained in 2013 with the lidar system developed there, but after that I think not much of data has been obtained, though it is potential to give, because atmospheric studies are, you have to build large database. It's not that you make a measurement for 1 month or 1 year, but unless you have a large database for over a number of years, you'll not be able to develop a model which is pertinent to a particular region or a locality. So that's why we are just showing here some of the typical data what has been obtained. And analysis of the data also is important here. The inverting the radar signal, as we see that what you measure is basically the intensity of the scattered signal. So from that you are supposed to derive the extinction caused by the particles or molecules in the atmosphere. So you are able to see the extinction coefficient of aerosol particles from the backscattered signal. So indirect way of measuring the physical parameters by measuring the scattering properties. So you require some inversion methods to do that. So here it's starting with a radar signal received power. So then you have to determine the beta and alpha values. So this is what we have shown with starting from way back in 80s. This some of the results here with a Ruby radar system. Okay, quickly run through that one. So here, of course, there's not this kind of, what I am suggesting is that those researchers who are interested in the atmospheric research, this is going to be a very good remote sensing tool for probing the atmosphere. So you have to build a lot of database in terms of clouds and then interaction of the clouds with aerosols with the clouds, and how it is affected by the background meteorological parameters, the temperature, water vapor, how they are affecting the cloud properties, that is the precipitation, thereby the precipitation also. So it is related to the monsoon properties, so then forecasting the monsoon arrival by making use of the study these things. So you require a large database. Here we built up some database on that one over a period of, and also another important aspect what we try to show here is the aerosol particles are not that they are generated locally all alone, because the atmospheric circulation will see that some of the aerosol particles are transported even thousands of kilometers. So what is being produced elsewhere, they are being transported to a different location. So what we observe here is not that they are generated here, but they're coming from elsewhere. So we did some measurements on that, the circulation, taking into consideration of the transport of the winds, and then how the aerosol particles observed or some pollutants, what is seen there, is now coming back to another location and detected by lidar system there. One incident I just would like to mention that there was sometime 2003, I think there was a color rain observed in Trivandrum, but there nobody knows what is the source for this color rain. But then when we observed the lidar data, we could see that coming from Sahara dust, some dust particles elsewhere are being transported to this location there. So that kind of transportation of aerosols also important, which can be studied making use of the lidar system there. Okay, next slide. Some of the satellite observations, yeah, quickly run through that one. So the transportation of some of the aerosol particles is also important here. Some minerals and then other pollutants get transported from one place to another, even hundreds of kilometers. The kind of observations are there. So okay, quickly run through that one. Okay, so now the making the ground-based radar systems is not alone sufficient for really developing a model. So what we require is to measure the clouds and aerosol properties from space, so that we have a global measurements there. So a global climate we would like to measure, and then that kind of the global climate change and a global level is possible if you are able to measure simultaneously from a satellite the different stations. So there are proposals already. NASA has launched a satellite with a cloud aerosol measurement, and similarly ISRO also has a program. I think these things we can go to the space. Next slide. Yeah, some of the other vegetation studies and all possible. You hear 11 news persons. This is a balloon lidar as a prelude to the spaceborne lidar. We had this kind of system which is being launched from the TFR facility here sometime back. Yeah, quickly run through that one. Now the ISRO has a program on this development of space-borne radar for to study. So this is the system configuration. A radar is now put in the space in a satellite orbiting around, I think, 800 kilometers, Earth orbit satellite. Now, when you send the instead of from the ground, now it is a reverse way. The radar transmitting from the top of the atmosphere, going to the top of the atmosphere, then tropopause, and then cirrus cloud, and then scattering volume, and then reaching the planetary boundary layer and the ground. So you have the signal like this now. You could see that the one corresponds to the top of the atmosphere, and as they go, that is coming down, that means more atmospheric particles are seen. So you have larger signal there. So it's the other way around now what we see, the signal levels here. Now the instrumentation part of it is, you have to, the most difficult part of it is to have a laser in orbit. So it has to be work in this space environment. So at that time, this was about 10 years back, 7 years back, the last cost of the laser was about 25 crores to have a space qualified laser source for this application. Next slide. So now you can see that when is orbiting here, so the footprint of the laser transmitter can be seen. So successively when the satellite is orbiting, so we'll be able to cover the same location after 14 days. So successfully you can see how the aerosol content or cloud content in the path can be measured here. So next slide. So these are some of the global change, the spaceborne radar instrumentation, and we observed clouds and then aerosol particles. So some of the specifications of the space radar system, where they make use of NDR laser, space qualified laser. And then the most important point here is that because the laser beam is traveling through the atmosphere about 800 kilometers from distance, so you need to have the laser divergence has to be reduced to a few micro radians. So that is similarly the receiver also has to match with that divergence of the field of view of the receiver has to match with the divergence of the laser, so that you don't collect much of noise. Only the signal, backchat signal only is collected. So that kind of instrumentation is to be flown in a satellite, because there is a premium on the power available for the radar laser source also in a space. So, but then with the new technologies and all, with more efficient lasers, compact lasers, today we have that kind of laser sources available for applications in the space-borne systems there. So now here we have just listed out the applications of radar in various areas like pollution modeling, then flood modeling, transport planning, then oil and gas exploration, high resolution imaging, transportation studies, surveys of road, rail, etc. So these are now being done because the technology of the laser source as well as the signal processing have improved, detection also has improved. So then you can see that today the applications are environment, meteorology, transportation, industrial safety, national defense like surveillance and all. So make use of the combination of hardware as well as software. It is not that hardware alone will give us the required result, because there is innovation techniques required here. Next slide. So some of the spaceborne systems which we measured, the Martian clouds, the ice content in the Mars, similarly law enforcement applications, then airborne radar, first line management, then transport planning, then mineral exploration. So then the recent advances in the making use of radar for autonomous transport. So the autonomous transport means that the vehicle has to move without any driverless vehicles there. So radar is now considered as rather used as a experimental observations are going on. So a driverless car is now tested for different by agencies, like Google also has tested. So making use of the compact radar, which is now available with a small size with low cost. Now they work up to 550 to 100 millimeter range. The radar provides the most precise sensor technology. It has significant advantages for camera and radar. So not that, so you need to have short and long range radar and camera system and ultrasound system and radar system. So a combination of these sensors is to be there to really work as a level 5 autonomy. Level 5 autonomy means that practically there is no driver. So it has to move in a public transport with a driverless vehicles. Now here it shows that the different sensors will be activated for a different measurement of different parameters here. In the black, what we are seeing, it is basically lidar measurement, emergency braking, pedestrian detection, and collision avoidance. So that means lidar is able to detect any obstacle in the path, and then it gives a measurement of that one, and then the radar will log a range, and then it gives the actual location of the particular obstacle there. So here the different sensors, what is the role of different sensors in the autonomous transport? So the cost as well as the size, and then the sensitivity to color, and then range. For example, lidar gives a longer range there. So, but then lidar alone will not work for this total thing. Because here is the comparison of radar and lidar, because lidar is basically a laser source, has less divergence. So whereas radar with a higher wavelength, so you have more divergence there. So then the footprint by lidar is very small, so you'll be able to resolve even any obstacle on the way, even smallest size you can detect by a lidar there. So, and also it is fast enough to give the feedback for any information for the driver, for the vehicle to change the course, its direction there. So some of the design considerations for this kind of autonomous transport is the range, resolution, speed, performance in different conditions, because they have to work in the fog conditions or rain conditions also with low visibility. So those things have to be taken care of. So these parameters are to be satisfied before you venture into driverless vehicle, because range resolution also very important. Now you could see that in the preliminary observations, the lidar is now mounted on the top of the vehicle. It is rotating all around to cover the 360 degrees, both front and back and side also. The horizontal field and then the vertical field are to be designed properly, so that you'll be able to see any obstacle when the vehicle is moving, so that the vehicle can take a correction, its travel correction there. Next slide. So here now the lidar design for these applications, there are two types of lidar systems are used. One is mechanical lidar, where we mount the lidar on the top of the vehicle and it will be rotating to cover the 360 degrees, because all around it has to see any obstacle is on the way. Now a single laser will do, and then but it will be short pulse, measuring time taken for the pulse to hit the target, return, scanning 360 degrees around the scene there. But then the capture full field it can do. We have another type of lidar system now, what is called flash lidar, where you have a number of a matrix of laser sources are simultaneously sent towards the target. So you have got a what is called the point clouds. That means each transmitter will give 1 point. So then you have the repetition rate is so high, like even 10 kilohertz. So then all of the lasers will be simultaneously transmitting. So you generate across the target, you have a point cloud. From the point clouds, you require a different type of software to generate the image. So the flash lidar advantage is that there are no moving parts, unlike the mechanical lidar, where it has to rotate around the vertical axis to cover the total azimuth there. In the case of flash lidar, it is a very reliable. At the same time, the field coverage is only about 30 to 40 degrees. That means you can see only where it is moving in the front direction, only 40 degrees in the azimuth. So that is a disadvantage. But at the same time, if it is a limited application where you require the vehicle to observe only about 40 degrees in the field of view in the horizontal azimuth, so it is sufficient there. Now the different types of signal processing, you can make use of the time of flight or even coherent sum like heterodyne detection. You can make use of to measure the actual signal. So there was a what is called the railway line between Kochuveli to Kasargod, some 531 kilometers. They wanted to have a very high-speed railway line. Towards that, lidar used for land survey to find out the what is the best the railway track to be designed and installed for this high-speed train. So then the next question is that the lidars can be used. Now lidar can be used as a sensor for flying taxis, what they call. So still this is also going on an experimental basis now. For example, Airbus has started one Vahana electric self-piloting laser aircraft. So it is a vertical takeoff, and then the radar will be scanning all around and then finding out any obstacle on the way. So this is the next slide. So like that, different here also. Then before landing, it will be making observation on the where to land properly, and then so the point cloud measurement will give the image of the landing space for the. This is a lidar made by Velodyne, so used by Airbus. Now the flying cars are not going to be far away. Maybe another decade time, it is going to happen. But this all happens because now the radar on a chip instead of the large size and all what we have seen for atmospheric sensing. For the autonomous transport, you have solid state radar, which is just, you can see the size of that one on a thumb here. So this is being used as a flash radar or a mechanical radar. So the cost of this one is very small now. So something people like say that $2,000. So this is the sensor used for autonomous transport, which is coming up now. So here, just quickly, we are showing some of the ground-based radars, big size, high-end radars, which are used for atmospheric studies, not for autonomous transport. These are being used in different locations, along with radar. So this is a big 2-meter telescope. So you can go up to about 100 kilometers, making use of this kind of radar systems for study of atmosphere, like its temperature profiles, gravity waves. This is a satellite-based radar launched by NASA. Basically to measure NDAG radar system, and then measures the clouds coverage and then aerosols at the global level, mainly for climate change studies there. So thank you very much for your kind attention.